The simplest way I can explain the concept of a wormhole is this. Try to picture a real earthworm eating its way through an apple. At one point, you'll see one part of the wormhole sticking through the top of the fruit, while its rear end is poking through the bottom. In this example, the worm itself acts like a tunnel, which connects two places in space, or two different places in time, or even a combination of both. In theory, a wormhole could help you travel to the same place you're at right now, but years ago, or instantly transport you to another continent. It can also help you travel back to when the ancient pyramids were being constructed. The concept was first theorized in 1916. Though back then, people didn't call them wormholes. It was then studied by Einstein and his fellow scientist Nathan Rosen back in 1935. But it all started with Einstein's theory of general relativity. He had a hunch that Isaac Newton's idea of gravity as a force wasn't completely right. So, he began working on many different experiments to prove his theory. In the simplest of terms, Einstein's theory of general relativity says that gravity is a curving or warping of space. The more mass an object has, the more it warps the space around it. Imagine a heavy ball resting on a trampoline. Because of the ball's mass, the rubber sheet under it is warped under the weight. It's the same with our sun. It's big enough to curb space across our solar system. That's why our planet and other objects surrounding us orbit around the star. Now, let's keep our attention on the same trampoline. If there's no pressure applied to it, its surface stays flat. Now imagine 2 points on this fabric, symmetrically placed on each side of the trampoline. Looking at them from this perspective, there's no possibility of them ever touching each other. But if an object is heavy enough, this flexible fabric can stretch so much that 2 points might potentially meet. The tunnel between those 2 points would be a wormhole. They're basically bridges that connect two places in the fabric of space and time that have no chance of ever meeting in normal circumstances. Wormholes can also be seen as shortcuts. Problem is, we don't have any of these wormholes in our universe, or at least none that we know of. Scientists have no proof so far that they exist, and we also don't have any idea how they can form to begin with. What we do know so far is that they could, theoretically, exist. To move forward with our story about wormholes, we also need to talk about black holes. They're points in space where gravity has so much force that even light cannot escape them. Gravity here becomes so intense that matter gets squeezed into a tiny space. We know that this can happen when a star, like the sun, is dying. At the beginning of their lives, a star's hydrogen ignites in its dense, hot core. Because of its gravity, it tries to draw in its own mass into a tiny point. But as long as it has the energy generated by hydrogen fusion, it also pushes objects outward. If we look at it this way, the life of a star is a delicate balance of forces that can last millions or even trillions of years. These forces are also the ones keeping our planet in place and making sure we move constantly at the same speed and trajectory. Once that star's energy is exhausted, the only force remaining is that of gravity. Hence, some stars, those that are big enough, become black holes.
Oh my God!
Since light itself cannot escape their force, we people can't visualize black holes. For the human eye, they're invisible. We need special tools with unique telescopes to help us point them out in the universe. Now back to the wormholes. We have yet to see what a wormhole looks like. But scientists have theorized that they are extremely unstable. Why? Because in simple terms, they're made out of a black hole and a white hole touching each other. Okay, what? And as far as we've studied them by now, black holes at one point become infinitely dense and the pressure becomes unimaginable. Once you enter a black hole, there's little chance you'll make it out the other side. Some astronomers say that even if we could find a wormhole, and we could technically enter it, and it would rapidly collapse on itself. Even the tiniest bit of extra mass, like that of our bodies for example, can result in the wormhole popping out like a rubber band that's been stretched too hard. So, wormholes, huh? We haven't seen them, but we do have some math that can back them up. Black holes? We can't technically see them ourselves, but we do have some gadgets that can help us with that. But there are some theories about the universe out there that might have caught your eye in the past too. If you've watched the movie Matrix, you might have heard about the simulation theory. This is one of those hypotheses that doesn't come from scientists, but rather from philosophers. We know that all the information we have surrounding us, sounds, images, texts, and textures of the things we touch are translated to us by our brains. If our brains are the windows to the outside world, who is to say we aren't living inside an illusion? It may sound outrageous, but some famous thinkers of the world have really considered this possibility. The simulation theory can't be listed as a truly scientific one. If it fails the basic test, there's no way to prove if it's true or false. What about life on other planets? There are many scientific projects taking place all over the world looking at ways humankind can survive outside the Earth, should we ever have to. Like the Hot and Mars project, which is taking place on Devon Island, located in the Canadian Arctic archipelago. Conditions here are so harsh that scientists believe if we can make it here, we can survive on Mars too. That's because the soil stays frozen throughout the seasons. Also, the eastern part of the island is covered by a thick ice cap all year round. Since almost no plants are growing here, there are no animals that could have adapted to these conditions. Despite all the scientific effort, some seem to believe there's some sort of life form on Mars already. NASA's Perseverance and Curiosity rovers take regular pictures of the reddish planet's surface. You can check out these pictures on the internet for yourself if you want to. Over time, some odd shapes have appeared here and there in these pictures, making some people believe people are living there already. Back in 2008, one of the rovers took a picture of a rock that looked very much like a female figure. Other photos seem to show animal-shaped figures, utensils, or other Earth-like objects. Again, there's little to no proof of this theory, as rocks can be of all sorts of shapes and sizes. And if you look at the pictures, it does make you wonder. We may find it hard to travel way over there, but we can theorize that our observable universe has an edge and an ending. This fact raised a question for many scientists and philosophers. Could our universe be just one of many existing in a multiverse? One possible scenario depicted to explain the multiverse is trying to imagine a bunch of universes as separate bubbles, constantly coming to be and moving. Since we haven't figured out all the features of the universe we live in, who's to say there aren't many more? As interesting as this theory might be, we have no observable evidence that we live in a world with multiple universes. So far, we can just imagine different bubbles of time and space, where the rules of physics might be different. Some might lack gravity, while others may exist without ever seeing the light.
Okay, so you've seen the movies and read the books on time travel. Most of them tell stories about entering some futuristic boxes, and in the blink of an eye, you're in some different epoch. For now, this is just sci-fi. But there are ways to make time travel possible, at least theoretically. We just don't have the technology figured out yet. For starters, time travel to the future could be achieved by traveling at high speeds, but not just getting a ticket on the superhighway kind of speed. This is based on Einstein's theory of special relativity. It explains that time slows down for objects that move at really high speeds. And the good news is scientists have already tested this theory, and it looks promising. They did it with the help of two identical clocks. One was placed on a jet, and one stayed on the ground. They found that the clock on the jet ticked slower than the one on the ground because of how fast the jet was moving. The faster an object is moving, the more time will slow down for it. Currently, the fastest speeds achieved by human technology are seen in a special type of particles called neutrinos. Some of these can move at almost the speed of light. At these speeds, 1 second for the protons is equal to 11 months for us. Now, we might be able to time travel to the future with the use of gravity, too. This idea is based on Einstein's findings, namely his theory of general relativity. Now, this theory explains that the stronger gravity is, the more slowly time moves. This means that as you get closer to the center of the Earth, the strength of gravity increases. And if you think about it like that, time actually passes more slowly for your feet than for your head. Now, is that why I'm always late for stuff? Good excuse. This effect has been measured too, with the help of the same strategy with two identical clocks. Scientists placed them on shelves at different heights and measured the rate of ticking. The clock on the lower shelf ticked more slowly because it experienced a slightly stronger gravity. But this option comes with a catch. To be able to travel to the far future, you'll need to find a place with extremely strong gravity, like a black hole. That's a point in space where the gravity has so much force that even light cannot escape it. There, gravity becomes so intense that matter gets squeezed into a tiny space. The closer you get to the black hole, the more slowly time moves. However, traveling via a black hole is very dangerous, mostly because it's a one-way ticket. Once you cross its edges, there's no coming back. Now, here's a fun fact. The GPS systems we use on our phones and in our cars already have to account for time dilation effects in order to work properly. That's because of the speed of the satellites they use and the gravity they feel here on Earth. Without these corrections, your phone's GPS wouldn't be able to pinpoint your location on Earth very precisely. Meanwhile, the third option has less to do with the universe's unknown forces and more to do with our own bodies. Scientists are trying to find ways to time travel to the future by slowing down the body's own processes. It's not time travel per se. You wouldn't technically be going anywhere. But if your body stays put for a long period of time, you could eventually wake up in the future. Some animals, like bears and squirrels, can slow down their metabolism during hibernation, which means they don't need as much food and oxygen to survive. Specialists are trying to figure out if humans can do the same thing. They're working on ways to make people go into a short-term hibernation for a few hours to begin with. This could be helpful for medical emergencies too, in order to help a person before they can safely get to the hospital. In 2005, scientists were able to slow down the metabolism of mice by exposing them to a small amount of special gas. However, when they tried to do the same thing with larger animals, it did not work as effectively. Our fourth option of traveling through time is really unique. It involves a special type of shortcuts that may exist in our universe called wormholes. Now, before we move on, let's try to understand what they are. You'll need to picture two balls and a trampoline. If there's no pressure applied on the trampoline, it stays flat. Now imagine the two balls placed on the trampoline symmetrically. If you look at them from this perspective, there's no possibility of them ever touching. But if you put enough pressure on the trampoline between the two balls, this flexible fabric can stretch so much that the two objects might potentially touch each other. The same thing happens with stars in different star systems. They're big enough to curve space around them. That's why most planets tend to orbit around a star. The tunnel between those 2 points would be a wormhole. These wormholes could be used to travel long distances, like 1 billion light years, or even visit different times. Now, many scientists, like Stephen Hawking, think that wormholes might appear and disappear, but be very small, smaller than atoms. The problem is that we don't know how to catch one and make it bigger so that people can use it. This would take a lot of energy, and we don't know if it's even possible. Some astronomers say that even if we could find a wormhole and enter it, it would rapidly collapse on itself. Even the tiniest bit of extra mass, like that of our bodies for example, can result in the wormhole slamming shut, like a rubber band that's been stretched too much. Now, the fifth solution for time traveling was proposed by an American physicist named Mallet. It involves one resource that we know for sure is abundant in the universe: light. The scientist proposed a theory about time travel that would use a rotating cylinder of light. He believes that if something was dropped inside this swirling cylinder, it could be moved in both space and time, similar to how a bubble moves when you swirl it with a spoon in your coffee. According to Mallet, the right shape of the cylinder could allow for traveling to both the past and the future. The physicist has been trying to raise money for an experiment to test his theory. This experiment involves dropping tiny particles, called neutrons, through a circular arrangement of spinning lasers. However, other scientists say Mallet's theory is impossible and there's no need to test it further. Well, even if we eventually figured out a way to travel back in the past or to the future, would it be safe? Scientists have been talking about a problem called the paradox of time travel for a long time. The main question is what would happen if you went back in time and did something that changed the future. However, a new study from researchers from the University of Queensland says that this problem might not be real after all. The scientists have done some calculations and found out that even if you had changed something in the past, the timeline would still end up the same way. Another variation of this problem is called the grandfather paradox. Imagine going back in time and preventing your own grandfather from having offspring. Come to think of it, it automatically means you shouldn't exist in the first place. If your grandparents didn't have your parents, how can you exist at all? Well, these days scientists are certain that even if you did experience something like that, you'd still exist in the present. That's because the timeline that already exists has a way of adjusting itself, regardless of where people are in time and what they do. Or somehow get 1.21 gigawatts in a DeLorean and make like Marty McFly.
Put on your shades because Mercury is a hotspot. From the surface of this planet, the sun looks 3 times bigger than it does from Earth, and the light is 11 times brighter. Mercury may spin slower than Earth, but it still knows how to have a good time. One day on this planet lasts a whopping 59 Earth days. But don't worry. A year on Mercury is only 88 Earth days long, so if you want to feel like a centenarian, just divide your age by not 0.25 or multiply it by 4. This way, you'll get your approximate Mercurian age. Easy peasy. And let's not forget about Mercury's funky orbit. For every 2 orbits around the Sun, it spins twice. That means each hemisphere gets a full year of daylight followed by a long night. Time zones would be a mess on this planet, so we'll just stick to GMT. Ugh, did anyone forget to take out the trash? Why does it smell of rotten eggs in here? Sorry, it's because we're on Venus now, and these stinky clouds don't smell like roses. Any planet's day is basically just how long it takes for it to do a full spin on its axis. Well, Venus takes its sweet time with this, way slower than Earth, in fact. So a day on Venus lasts a whopping 243 Earth days, or almost 6,000 hours. Now here's where things get a bit tricky. Because Venus's day is so long, we actually use Earth's day as standard for keeping time on the planet. That means there's only one time zone for the whole planet. Seems convenient, huh? Venus's year is about 225 days. So if you were celebrating New Year's Eve on Earth in the year 2000, that would have been Venus's year 3251. So to keep track of time of Venus, we can use the local year, made up of 225 Earth days, but every 3 years or so, there's an extra short year made up of only 224 days. Not that confusing. We have leap years on Earth too, but it works a bit differently. We've made it to planet Earth. Woohoo! How many time zones do we have on this big blue ball? Give me a drum roll. 24. And did you know that we can actually mess with time a little bit? Yup, in about 80 countries, mostly in Europe and North America, we have something called daylight saving time. It's where we move our clocks forward an hour during the summer so we can soak up all that sweet, sweet sunshine. But beware, each country has its own rules about DST. So make sure you don't get caught snoozing when you're supposed to be working. And get this, some regions even have time zones that differ from UTC by half or quarter-hour increments. Can you imagine that the moon is getting its own time zone? The European Space Agency announced on Monday that it's time for the moon to have its own synchronized time zone. With more and more countries and private companies planning missions to our lunar neighbor, it's important that we all speak the same language when it comes to timekeeping. Right now, each mission carries Earth's coordinated universal time with it, which is fine when there are only a few missions happening at once. But with dozens of moon missions planned over the next few years, things are going to get tricky. We need a system in place to make sure everyone's on the same page, or we'll end up with different spacecraft out of sync with each other, and nobody wants that kind of chaos in space. Precise timekeeping is super important for communication and navigation, so we need to figure out a way to make sure everyone's on the same page. The ESA hasn't figured out exactly what form this new lunar time zone will take, but they're working on it. Should there be a single organization responsible for keeping lunar time? Or should we let the moon set its own time? And what about more granular time zones based on the sun's position? These are all important questions that need to be answered. When it comes to a day on Mars, it's not too different from a day on Earth. We're talking 24 hours, 39 minutes, and 35 seconds. A Martian year is 1.8 Earth years, which means the Earth year 2000 happened in Martian year 1063. Almost forgot. The Martian year has 668 local days. Phew! We sorted out the Martian calendar, but Mars will need local time zones. Because of its elongated orbit, the difference between summer and winter hours will be significant. Daylight saving time will be a thing on Mars. A year on Jupiter lasts almost 12 Earth years. Yeah, that's like a lifetime in dog years. But don't worry, they've got 12 seasons to keep things interesting, each almost as long as an Earth year. But a day on Jupiter only lasts 9 hours and 55 minutes. Also, since Jupiter doesn't have a solid surface, the clouds move at different speeds, so two free-floating atmospheric stations could experience different days. Hey, if we lived on Jupiter, we'd be in bad need of some cool app tracking all those things. Anyway, if we ever terraform Jupiter's region, most of the population will still live on Jupiter's moons, because the atmosphere is just too wild. And get this, the moon's revolution periods are connected, so we can use the same day counting system for all of them. On Io, we can have 2 standard Jovian days in 1 Earth day. How do we break that down? Well, we could have a minute of 53 seconds and an hour of 103 minutes. Or we could just stick with Earth's minute and hour and have a day that's 21 hours and 13 minutes long. How old are you? I'm 200 days old, and you? Sounds odd to you, Earth dweller, but dudes on Saturn count their age in days. A year on Saturn is crazy long, like more than 29 Earth years. Kiddos would only get a fraction of a year, while the oldest folks might get a whopping 3 years. So to keep track of time on Saturn, we could divide up a Saturnian year into 29 or 30 seasons. Oh, and fun fact, Saturn doesn't even have a solid surface, just rotating clouds that spin at different speeds. But we could still set up some cool research stations or helium extraction balloons to float around up there. 1 Uranian year lasts a whopping 84 Earth years. So to make things easier, we'll stick to using Earth years for our calculations, and natural Uranian years can be used for special occasions, like reaching 1 Uranian year old. As Uranus doesn't have a solid surface, the rotation period is all over the place. Only science missions and helium mining companies are brave enough to venture into the atmosphere. And get this, each moon has its own day and date system. Pretty confusing. Most people won't ever celebrate 1 Neptunian year old. 1 year on Neptune is like that's way too long for us humans to stick around. But don't worry, we'll still bust out the confetti and party hats for special occasions, like when it's been 2 whole years since the first spaceship hit up Neptune. As for the rest of the time, we'll just use Earth years for all our business needs. Pluto takes a whopping 240 Earth years to orbit the Sun, which is way too long to use as a year in our everyday lives. A day on Pluto is almost like a week on Earth. So, to keep track of time, we're going to divide that into 6 standard Plutonian days, 3 of light and 3 of dark. That means a standard day on Pluto will last slightly more than 1 Earth day. Now, because Pluto's axis is super tilted, using time zones would be pointless. So we'll just use 1 time zone for the whole system. Easy peasy. As for the standard Plutonian year, it'll be almost the same as the Earth year, about 343 days. But once in 10 years, we'll throw in an extra day just for kicks. That's all for now. See you on Pluto.